Nature Hacker, and this is your world. So today I'm going to teach you how to make light. Now, that statement might boggle your mind. Like, well, how could you create light? How can you make light? Well, it's pretty easy. Just think, how do lights work? What is the principle that underlies all lighting? Be it fluorescent lights, incandescent lights, LEDs. What are they all doing the same? And most people will be like, well, I don't know. It's basically exciting atoms, right? Something like that, exciting atoms. But that is not actually accurate. And in order for you to innovate and create light in more efficient ways or more powerful ways or whatever, you have to know exactly what's going on, because the more you understand, the more you're able to innovate. It's the reason why I was able to innovate a new type of battery and a whole range of possible batteries, is because I had a better understanding of batteries than anyone else. So it's the same with light. Now we can innovate more types of lights because we will now know how light is actually made. So the first thing you have to understand is that light is a form of matter of energy. So energy has at least three forms of matter: solid, liquid, and gas. The solid form of energy is chemical bonds. So like covalent bonds or things like that. So that's a form of solid energy. Liquid energy is electricity. Okay, it like flows through conductors. And gaseous energy is light. And so this lines up with all experiments. There is no experiment showing that light and electricity are different entities. Light, electrons are just made up of light. They are literally made up of light. It's just a solid form of photons. So it's all photons. Energy is all photons. Just like water, ice, and water vapor is all the same exact thing. It's just in a different form. It's like, yeah, water vapor, if you were really big, if you were a giant and you're looking at water vapor and water and ice, you would say that they're three different things. But if you could zoom in, you could see that they're all made up of exactly the same thing. And just like a drop of water is a bigger chunk of condensed water molecules, and gaseous is like, expanded water molecules. So it's the same with electricity or electrons and light. Electrons are just bigger droplets of photons. Light is more, what do you call it? Evaporated state of photons. So that's what we're dealing with. So now we can understand how to create light, and how to create light is evaporate electricity. If you don't know that, you will never innovate a new light design, okay? You just can't. How can you? If you can't understand what the principle is working on, how can you innovate? How can you create something new? You can't do it. You could get lucky, maybe. And that's how all of these other lights were invented. People just got lucky. They didn't really understand what they were doing. So, yeah, so what's the most basic way to evaporate something? I mean, you increase temperature and you decrease pressure, right? Like, let's say I'm boiling something and I put a vacuum pump on top of it. It's going to boil at a lower temperature than, it'll boil easier. Like, let's say I'm heating up water and the water is at, it's like at the heat of a, it's just room, let's say it's room temperature, right? So water is not boiling at room temperature. Why not? Well, boiling is the process of converting liquid water into gaseous water. Okay. So what's happening is there's enough pressure in the atmosphere that is pushing down on the liquid water and saying, no, you can't evaporate. You can't just spray off in all directions as a gas. You have to be contained as a liquid. But when you lower the pressure, you allow more gaseous water molecules to come out of the water, right? So if you have electricity or even bonds, and you lower, see, well, let me just say this really quick. Bonds are solid, right? So if you're going from a bond straight to light, that's sublimation of photons. That's photon sublimation. And it's usually not as good. That's why things that glow are sublimating light. So it's not as, like, potent of a, what do you call it? It's not as potent of a light source, obviously, because it's harder to make a lot of photons sublimate than it is to evaporate a lot of photons. But it's probably going to be more energy efficient to sublimate than to evaporate. You know, sublimate is going from a solid straight to a gas and not into a liquid first. So it's going straight from bond energy into light. So that's a pretty efficient way to go about it, and I feel like a lot of biological things actually use sublimation of light, because it's hard to harness electricity. Electricity is a liquid, so it's like you have to have some conductive pathways in order to have electricity flow, you know. So, you know, like metals, basically, you have to have like solid metal practically to make electricity flow, and then convert that to light by making it evaporate. And that's what I'm getting to now, is how to make light evaporate. Well, it's just like making anything evaporate. You have to, well, first of all, you have to have a high concentration. One, you have to have a high concentration of your stuff, right? Of your liquid, let's say. Two, you have to have a low pressure above that liquid so that the molecules can go off into gaseous form. So you have to have a high concentration. You have to have a low pressure. And there's one more thing. Oh, and high temperature. So you need high concentration, low pressure, high temperature. So all of those things, like let's say I have a lot of water, and I have a vacuum pump running, so it's a low pressure, and I'm heating it, so it's a high temperature. That's the perfect trifecta of making liquid water into gaseous water, right? Exactly, and that's exactly the same way we make liquid light, electricity, into gaseous light, photons. So the way, so it's pretty simple. I mean, that's really it, is those three factors: high concentration, low pressure, and high temperature. So how do we make a light? Well, we need a high concentration of electrons, you could call it, or electricity. So we need something like, let's say we have a gap, right? Here we have a gap. So we need a high concentration of electricity. So that pathway needs to be conductive, so that the electricity flows across that gap to some extent. So there's going to be a lot. Let's say if the electricity is coming from here and it zaps over that way. So this pathway needs to be conductive as possible, but it can't be purely conductive, or else we're not going to get evaporation. So it goes into our next components. So we need a lot of electricity there, okay? So that this pathway needs to be conductive. Now, secondly, we need a low pressure. We need a low pressure. So just a vacuum, like an incandescent bulb uses a low pressure by creating a vacuum in there. So yeah, what are the other forms of light? LEDs, they create a low pressure by having holes. In a semiconductor, there's holes. It's a P-type semiconductor and N-type, so the N-types go into the P-types, and it fills these holes. So there's a low pressure there, basically, the equivalent of a low pressure. I don't know, maybe they also have a vacuum in their little LED thing. So we need a low pressure, just like a vacuum, Yeah, so that will help. Also, fluorescent lights obviously have a low pressure. They are basically vacuum tubes, fluorescent lights. So we have a high concentration with a conductive pathway. We have a low pressure with, like, a vacuum in the bulb or whatever. And thirdly, we need a high temperature. So we need to heat up that electricity, or the atoms that are, conducting that electricity to high temperatures. So an incandescent bulb, the flow of electricity heats up that filament really high, allowing a lot of light to evaporate off. LEDs, they don't really use high temperatures, but maybe they could improve from high temperatures. I mean, because usually evaporation happens at higher temperatures, so that might be something that they could try, I guess. And fluorescent bulbs, um, they don't really use high temperatures much, but again, they might benefit from a higher temperature. Maybe they just don't have this knowledge, so they were just lucky hit and miss um, on the results they've gotten. So maybe if they increase temperature, they could get more light output. And it could be different. It could be different with light. It could actually be more efficient at lower temperatures, but I highly doubt it. I think that all three of these factors work together, so maybe they can work if they don't have all three factors, as long as they have one or two. It's like the light bulb doesn't really have it's not really jumping across a gap. It's going through a conductive piece of metal, so that's not quite as good as it could be. A fluorescent bulb doesn't use high temperatures, but it does use a conductive pathway, and it does use low pressure. So it's like they might be getting 2 out of 3 right, but if they got all 3 right, they could be more efficient, possibly. So I mean, that could be a way to go about it. Is let's try hot LEDs, let's try hot fluorescent bulbs, and maybe we will get better results. So yeah, and instead of a semiconductor filament, let's use a semiconductor filament in an incandescent bulb. That way we can get gaps that the electricity has to jump. So, and that's another thing is, as far as the conductive pathway is concerned, what it's doing is it's creating a gap for the electricity to jump, and that is a really easy way to create light. You just give it a gap and it'll jump a spark. When you have a wire where electricity is flowing in it, it's not like lighting up or anything, but when you give it a gap to jump, like where it's spark gap, you get light. It's not that efficient of light. And so that's our basic light, is a spark gap. Now, what we can do to improve that is, instead of it jumping once, we could have it jump a bunch of times. So we could have, like, a big assortment of copper wires, so it's jumping 5 times instead of 1 time across. There's 5 sparks going across instead of 1. So that's one way to improve efficiency. And basically, that's changing the surface area. That's basically what that's doing, is just making a greater conductive pathway surface area type thing. It's giving electricity a greater conductive pathway. So that was our first step there. So that's how we could take a spark, increase it, is 1, improve the conductive pathway. And it's not that you want the most conductive pathway, it's that you want the greatest kind of area of conductive pathway, so to speak. So taking our spark gap, with our knowledge to improve it, we can increase the surface area of the spark, increase the size of the spark, basically, the area of the spark. 2 is we can decrease the pressure, so we can put it in a vacuum. And 3 is we can increase the temperature. So, yeah, we can increase the temperature of that system to help the light evaporate better. So there might be other factors like magnetic strength and things like that. One thing that magnetic fields can affect is one thing that magnetic fields can affect is, I don't really know. Oh, the conductivity of the pathway. So we can use a magnetic field to make that pathway more conductive, so we can get more electricity building up on, the conductors, basically. So yeah, magnetic fields is going to definitely be something to look at as far as in light creation. So yeah, so there's some factors to think about, and now this is the real understanding of how light is created. And you could also think about how God created light. Like, let's say we take the Bible, and on this seventh day, I guess, God said, "Let there be light." So what He could have done is created a potential difference between the sun and the solar system, for example, or other. He creates a potential difference. Like, let's say, things are already orbiting the sun and whatever, and let's say He charges the sun up, like he's like bzzz, charging up the sun. Okay, while you're charging the sun, create a vacuum in space. Let's say space wasn't a vacuum before. Okay, whatever. Create a vacuum. So let's just say the process of creating light. So you charge up a sun, you create a vacuum, you suck a vacuum. So that's decreasing the pressure, charging the sun, which is increasing the amount of electricity, decreasing the pressure with creating a vacuum, and then increasing the temperature. And then you need that basically, and then there's a magnetic field which can transfer, that can help increase the conductivity of space so the electricity can transfer. So what's happening is the sun is, you've seen those the plasma globes, where it has that thing in the middle and there's these plasma streams going off into the glass around it, right? So that's what the sun is like. There's streams of energy going from the sun to all of the planets and asteroids and everything in the solar system. So there's this energy being streamed out, and the energy is being streamed out, and it's going out and it's evaporating. The energy is evaporating because of the low pressure, because of the high temperature, and because of the high surface area of transfer. You want that, like in a plasma ball, you want those streamers to be as thick as possible, and what would be best is them to be just fully thick, so it's just 360 degrees of plasma going around there. You want that area of of energy flow to be as great as possible. So that's how the sun works. That's how it creates light, is that energy is being transferred through to the solar system with a high surface area of transfer. There's a high amount of charge differential, so that there's a differential in charge, which is a voltage basically, and you have a high temperature. So the sun is very good at creating light from electricity, say. So I hope that makes sense. You're hearing it here first. I mean, this is really cutting edge, and with this knowledge you can go and make better lights than have ever been made before. So thanks for watching. I am the Nature Hacker, and like I always say, go do work, which means take this information I give you and use it to create something new. Use it to an elevated understanding to change the world for the better, okay? To change the world for the better. So take this knowledge and invent a new light bulb, alright? Thanks for watching. I am the Nature Hacker. Do work.